Welcome to The Explainer. Today, we're going to pull back the curtain on the one secret ingredient that lets AI solve incredibly complex problems. It all comes down to a tiny decision, a little spark, that turns what's basically a simple calculator into a machine that can actually learn. Let's dive in.
All right, so let's kick things off with a puzzle. You'd think if you just stack a bunch of simple parts together, you'd get something really powerful, right? Well, with the very first neural networks, that's not what happened. You could add more and more layers, but they just couldn't learn anything more complicated than a straight line. So, what was going on?
Here's the thing, without the secret ingredient we're talking about, just adding more layers to a network doesn't actually make it any smarter. Imagine stacking a bunch of perfectly straight rulers. No matter how many you pile on, all you end up with is another, thicker, straight ruler. This big roadblock has a name: linearity. It basically means the network is stuck in its ways. It can't learn curves, it can't learn corners, it can't figure out any of the messy, complicated relationships you find in real-world data. Things like telling the difference between a cat and a dog, or, recognizing a face in a crowd. So how do we get a network to see the world in curves instead of just these boring straight lines? Well, we introduce a little spark of nonlinearity after each and every layer. And in the world of AI, that crucial spark is called an activation function. These functions, they're the whole secret sauce. They're like little gatekeepers at the end of each layer. They look at the signal coming through and decide, is this important enough to pass on to the next layer? And it's that simple act of deciding that introduces the nonlinearity AI needs to do complex learning. And get this idea is so powerful. It actually has its own theorem, the universal approximation theorem. It's a mathematical proof that says with just one of these nonlinear gatekeepers in a hidden layer, a network has the power, at least in theory, to learn pretty much any pattern. This is the bedrock of modern AI's power. Okay, so let's actually meet the three most common gatekeepers that are powering modern AI right now. Each one has its own personality, its own vibe, and a very specific job that it's just perfectly suited for. First up, we've got Sigmoid. This is one of the originals. Its job is super straightforward. Take any number you give it, I don't care how big or how small, and squash it down into a value somewhere between 0 and 1. And that makes it absolutely perfect for representing a probability. Yeah, its whole vibe is about certainty. How sure are we? You'll almost always find Sigmoid in the very last layer of a network that has to make a clear yes or no decision. It spits out a number, like 0.98, and we can just read that as, okay, I'm 98% sure. Next up is Tan. You can think of it as Sigmoid's more balanced cousin. It also squashes numbers, but it squashes them into a range between -1 and +1. And this ability to represent negative, neutral, or positive signals, well, that gives it a pretty cool advantage. Right, because its output is centered around 0, the signals coming out of a tanh layer are much more balanced. This helps the next layer in the network learn a bit faster and a bit more stably. It's why it's a really popular choice for hidden layers, especially in fields like financial modeling, where you're dealing with both gains and losses. And finally, we get to ReLU. That stands for Rectified Linear Unit, but everyone just calls it ReLU. This one is the undisputed king of modern deep learning, and its rule is, honestly, it's almost shockingly simple. ReLU's whole philosophy is this: if an input signal is negative, it's probably not useful, so the output is just 0. It kills the signal, dead. But if the input is positive, it says, go for it, and passes it through completely unchanged. This brutal simplicity is its superpower. It makes it so fast. So let's just quickly recap the main takeaway here. Each of these gatekeepers has its own special job, right? You use Sigmoid at the very end when you need a clear probability. You might use tanh in the middle layers when you need to handle those balanced positive and negative signals. And for pretty much everything else in modern deep networks, you use ReLU, all because of its raw speed and efficiency. But it wasn't always this way. Those early gatekeepers, Sigmoid and Tan, they had this hidden critical flaw. A flaw that almost killed the entire dream of deep learning before it really even got off the ground. The problem is called the vanishing gradient. Okay, gradient sounds technical, I know, but all it really means is the learning signal. It's the message sent backwards through the network that says, hey, we messed up, let's make a correction. With Sigmoid and Tan, that message gets squashed at each layer, especially on the flat ends of their curves. The signal gets multiplied by a number close to 0 over and over again. And after just a few layers, poof, it's gone. The earliest layers get 0 feedback, and the whole learning process just grinds to a halt. And this one problem was so bad, it actually contributed to a period in AI history we call the AI winter. For more than a decade, progress just stalled. A lot of people thought truly deep networks were simply impossible. That is, until 2012. That's when a network called AlexNet had a massive breakthrough, all powered by our new hero, ReLU. ReLU's simple design was the key. Because it doesn't squash positive numbers, that all-important learning signal could flow backwards through many, many layers without just disappearing. This one simple change is what finally unlocked the true awesome power of deep networks. But hey, even the king isn't perfect. ReLU solved the massive vanishing gradient problem, but its aggressive kill signal created a new, though thankfully much less common issue, the dying ReLU. This can happen if a neuron just gets unlucky in its internal mass shifts, so its output is always negative. It gets stuck in the off position permanently. It basically dies and stops contributing to the network at all. So even with these little quirks, researchers have figured out how to use these gatekeepers really effectively. But why does any of this matter to you? Well, because these simple decision makers are working behind the scenes for you every single day. Let's see how. Think about it. Every single time you swipe your credit card, a network just like this is analyzing that transaction. The hidden layers, probably running on fast ReLUs, are hunting for any weird nonlinear patterns. Then, that final output layer uses a sigmoid to spit out a single probability score. If it hits, say, 0.98, your bank blocks that transaction in milliseconds to protect you. And this idea of pairing the right tools for the job is everywhere. The networks that recognize faces in your phone's photo gallery, they are packed with efficient ReLU layers. Models trying to predict stock market trends, they often use TAN because it's great at handling gains and losses. And that final layer will almost always use something like sigmoid to give you that one clear final answer. So if there is just one thing, one core idea you take away from all this, let it be this. Adding just one of these nonlinear sparks. That is the fundamental difference between a simple calculator that only sees straight lines and a machine that can actually learn from the complex, messy, and curvy nature of our world. It's a powerful thought, isn't it? That from these simplest possible decisions, on or off, pass or block, this immense complexity and intelligence can just emerge. It kind of makes you wonder what other huge, complex systems out there are built on foundations that are just as simple. Anyway, that's all for this explainer.